Hello everyone, my name is Shruti Kesri. I'm working as Assistant Professor in Computer Science Department in ABES Engineering College, Ghaziabad. Today I'm going to discuss some GATE questions based on Dijkastra algorithm. This question is given in GATE CSE 2012. Question is like, consider the directed graph shown in the figure below. There are multiple shortest paths between vertices S and T. Which one will be reported by Dijkastra's shortest path algorithm? Assume that in any iteration, the shortest path to a vertex V is updated only when a strictly shorter path to V is discovered. As we already know about the Dijkastra algorithm is used to find the shortest path between two nodes, or you can say that this is single source shortest path algorithm. Here, your source is given as S, and you need to find out the path which is the shortest one from S to T. T is the destination part and S is the source. Yes, there are various paths from S to T like SDT, SBDT, SACDT, and SACET. We need to find which one is the shortest path. And for that, here, this is giving the relaxation process, that is, in any iteration, assume that in any iteration, the shortest path to a vertex V is updated only when a strictly shorter path to V is discovered. Let's see how to solve this question. Here, I'm taking two tables just to define the values according to the Dijkastra algorithm. First is defining the weight of each and every node, and second is defining the parent of that particular node. It means parent means how to reach that particular vertex. This is defining by the parent table. Here, I'm just taking S as a starting node. It means source node. So providing the weight 0 and give all the vertices at infinity. This one. These are the vertices in the given graph. Now, you need to use Dijkastra algorithm, and Dijkastra algorithm use greedy algorithm. Greedy algorithm means which is the local optimum value, right? Then according to your given graph, S is having three edges starting from this one. One is going for the A, that is containing the weight 4. Second is edge from S to D, which is containing the weight 7. And third is from S to B, which is containing the weight 3. Then according to the relaxation process, currently the weight of A, D, and B is infinity. But relaxation is saying that if a particular node, weight of particular node is greater than the node U plus weight of U and V. This is saying just if you have an edge from S to A, and V stands for the A, and the weight of this A is infinity. This is greater than the edge is starting from the S, and the weight of the S is 0 plus weight of the edge from S to A, that is 4. If infinity is greater than this value, then relax the vertex A and update this value by the given value. So we'll update this value here just by putting the value 4. Similarly, in case of D, current value of D is infinity. Let's check if we are moving from S to D and calculating the value, that is 0 plus cost of edge is 7. Then 7 is less than infinity. You can relax the value of D also, that is 7. Similarly, in case of B, current value is infinity, but when we are moving from the S to B, you need to add 0 plus 3, that is less than infinity. Update the value as a 3. Now again, S is already visited. Put the parent of A, B, and D as S. This one. Now again, which one is the lowest value? In A, B, C, D, E, F, G, T, B is containing the minimum value, right? Now choose B as a visit B and check all the adjacent nodes. There are two edges starting from the B, one from B to D and second is from B to S. As S is already visited, no need to go for that. Just check the value from B to D. Currently, D is containing the weight of 7. If we are going from the B to D, then current weight of B is 3 plus weight of H from S from B to D is 4, that is 7. Both are equal, so no need to relax the weight of your vertex D. It will become same value and no need to change the parent of D also. Now B is already visited. Now which one is the least value? 4 and 7. In between 4 and 7, 4 is the minimum value. You can say A is containing the lowest value. Now check the A value. A vertex is containing only one edge which starts from A and going for the C vertex. Now currently the weight of C is infinity. Then check if we are going from A to C, what will be the weight? Current weight of A is 4 and the edge of from A to C is containing the weight 1, that is 5. 5 is less than infinity. Relax the vertex C. Now this one is given and the parent of C is A because you are reaching at level 5 of vertex C by using vertex A. Now A is already visited. Now you have C, D, E, F, G and T. In these, C is containing the minimum weight. Just choose the C. From C, there are two edges, starting two edges. One is from C to E and second is from C to D. Let's check. Current weight of E is infinity. And when moving from the C to E, weight of C is 5 plus weight of edge from C to E is 1, that is 6. Infinity is greater than 6. Relax the edge E and put the parent of E as a C. Now, let's check for the D. D is containing the weight of 7. And when we are moving from C to D, in that case, C is containing the weight 1 and edge is containing the weight 3. That is 8. 8 is greater than 7. Then no need to change, no need to relax the vertex D. Now, which C is already visited. In D and E, F, G and T, E is containing the least weight, visit E. From E, there is only two edges starting from one E to G and second is E to T. G is containing the infinity weight and when we are going from E, the weight will be E is containing the weight of 6 plus 2, that is 8. 8 is less than the infinity. Update the value of G. Now we are talking about the T. T is also containing the weight of infinity. When we are moving from E to T, E is containing the weight 6 plus H from E to T is containing the weight 4, that is 10. 10 is again less than infinity. Relax the value of T. And update the value of parents of G or T as E. Now it's also visited. Now D, F, G, T. In this, D is containing the least value. Then visit this D. From D, there is three edges. From D to E. Second is D to T. Third is D to F. But E is already visited. Then no need to go for that. Check for D to T. T is currently containing the value as 10. Right? And F is containing the current value, that is infinity. So let's check for the relaxation of this T. T is currently containing 10 value. When we are going from D to T, D is containing the value 7 plus the weight of H from D to T is 3, that is equals to 10. Both are same. No need to relax the value of T. Now we are checking for the F. F is currently containing the value infinity. Then go for D to F. D is containing the cos 7 and the edge is containing 5 weight, that is 12. 12 is less than infinity. Update this value and put the parent of F as D. Now, checks another one. Already D is visited. Mark D as visited. Now in FGT, G is the smallest value containing the smallest value. Check for this one. From G, there is two edges starting. One is from G to E and second is from G to T. But E is already visited. No need to go for that edge. Check for the value of T. T is currently containing the 10 value. When we are going from G to T, G is containing the value 8 plus edge cost is 3, that is 11. T is already containing the 10 value and 10 is less than 11. So no need to relax the value of T. Now, G is already visited. Check for the T. From T, only one edge is starting from here. That is T to F, which is containing the weight 5. Check for the availability of F. F is containing the weight of 12. And when we are going from T to F, T is containing the weight 10 and the edge is containing the cost of 5. Total cost will be 15. But F is already containing the value 12 and 12 is less than 15. So no need to update this one and just mark this as a visited. Now F is only the rest value. No need to check because all other vertices are already visited. This table is showing that from S to A, minimum cost is 4. From S to B, minimum cost is 3. S to C, 5, S to D, 7, S to E, 6, S to F, that is 12, S to G, that is 8, and S to T is 10. Then we have this question that we must have multiple values. From S to T, we have multiple paths, but what is the minimum cost? Now just check the value path from S to T. Just go for the parent value. T is containing the parent value of E. Now, E is containing the parent value of C. Now, let's like this one. We need to rub here. Now, again, I'm writing this one. You are getting T value from E. We are checking this value from the parent table, this one. And we are getting this value E from the C. And now check the value. Who is the parent of C? That is A. And now this is giving the value S. Parent of S, A is S. You have a path SACET, which is containing the shortest cost, or you can say shortest path. Now let's check the previous example. In this options, which one is the least value? That is SACET. Even though these are visiting multiple vertices, but the cost is the shortest cost. So in this question, your answer will be D. Now, let's take another example. This question is given in CS 2008 GATE question. In this, Dijkastra single source shortest path algorithm, when run from vertex A in the below graph, computes the correct shortest path distance. First condition, or you can say first limitation of Dijkastra is that you can only apply Dijkastra when the weight is positive. What is the negative part? Why we are not considering the negative part? Because it can be possible, there is a limitation in Dijkastra that if once you have visited a vertex, after that you cannot revisit that vertex, right? So in that case, sometimes Dijkastra will not give you the optimal solution because we always go for the optimal solution. So in that case, it can be possible that if edge is negative, in that case, your shortest path will not be the exact shortest path, or you can say optimal solution that particular problem. But before going for that conclusion, we need to check it. And this is the question about this one, because it's this graph. If you are looking at this graph is containing the negative weight also, right? So before answering this question that no, this will not be applicable because this is containing the negative weight, just apply the Dijkastra algorithm. Let's see that is this negative weight is again updating the value of previous visited one or not. If it is not updating, if it's not updating, affecting previous value, it means this time Dijkastra is giving the optimal solution even after that weight is negative. So in this question, no need to go direct for the direct conclusion that no, this is not applicable in Dijkastra algorithm. Just apply the algorithm. Now let's see how to apply this one. Again, I'm taking this one. Here, one is defining the weight of all the vertices, and second is defining the parent of that vertices. Now, A is the starting node. you have only one edge from A to B, and it is containing what? The cost of edge is 1. B is currently containing the cost of infinity. So just check the relaxation process. If we are going from A to B, A is containing the cost of 0 and the edge cost is 1. That is 1. Yes, 1 is less than infinity. Relax the value of B and put the parent as A. Now, from B, you have only one edge which is moving from, sorry, you have two edges. One is moving from B to C and second is from B to E. Now, just check the value. C is containing the value infinity. If we are going from the B to C, B is containing the cost of 1 plus edge cost is 2. That is 3. Yes, 3 is less than infinity. Relax the value of this one and update this value as B. Now, let's check for the E value. Currently, E is containing the value of infinity. And when we are going from B to E, B is containing the cost of 1 minus 3 is equals to minus 2. Now, E is containing the cost of minus 2 and parent of E is B. This one. Now, which one is the minimum value? Yes, A and B is already visited. You can mark this one. A and B is already visited. In C, D, E, F, G, H, which is containing the minimum value? E is containing the minimum value. From E, you have only one edge starting from E to F. When you're talking about the E to F, F is containing the cost of infinity. But when we are moving from E to F, E is containing the cost of minus 2 and plus the weight of that edge from E to F is 2. That is 0. 0 is less than infinity. Relax the value of F and put the value as a parent of E. Now, which is the minimum value? Again, E is visited. C, D, F, G, H. Yes, F is containing the minimum value. Now, just go for the F. F is also containing only one edge starting from this one and going for the G. G is currently containing the cost of infinity. And check for the relaxation process. F is containing the cost of 0 plus the edge is containing the cost of 3. That is 3 total. And obviously 3 is less than infinity. Then update the value of G and update the parent of G as F. This one. Now, G is already visited. Mark is at, sorry, F is already visited. Mark is at this one. Now, in C, D, F or H, C and G is containing the same cost. You can choose anyone. Here I am choosing the C. From C, there is two edges starting. One is from C to H and second is from C to D. Let's check for the C to D. Current cost of D is infinity. When we are moving from C to D, it will be the cost of C is 3 plus the cost of H from C to D is 3. That is 6. And 6 is less than infinity. Update this value as 6. Now we will check for the H also. H is currently containing the infinity value. But when we are moving from C to H, C is currently containing the cost of 3 minus cost of H, that is minus 5 is equals to minus 2. Minus 2 is less than infinity. Update the value as this one. And also update the parent of this one. That is what? This is C and this is C. This one, C is now visited. Now let's check for the minimum value. Now this time minimum value is H. H is containing the minus 2 value here. Now check for the edges starting from the H. H from H, you're only one edge that is starting and it's going for the H to E. But E is already visited, so it will not update any value. It is already just visited. Now, in D and G, which one is having the minimum value? G is having the minimum value. Just check for the other one. From G, you have two edges. One is from D to E, but E is already visited. Then no need to go for the relaxation of E vertex. Let's check for the H. H is containing the cost. H is already visited. Then no need to go for this one also. So G will get visited, but it will not update any value. Now let's check for the D. D is the last value. This will not get updated. Here you can see that due to negative weight, there is no cycle, or you can say no other vertex it get affected, even though that edge is containing the negative weight. So in that case, when we go for the question, what will be the answer? It's saying that this from using this graph, if we apply the Dijkastra algorithm, which one will be the right choice, correct shortest path? So here you can see that all the vertices are getting the minimum value. No such type of vertices are there which will get affected just because of negative weight, right? So here answer is D. I think you all have cleared about Dijkastra algorithm, how to use this one and how to solve these questions. Thank you.